This is Mr. Sitta. I'm going to run through the answers to the review packet on thermochemistry. And I think I happen to have two of these. Okay, yeah. All right, so this is the 2020 version. I think I'm going to end up giving you both to look at to practice for the test. So I might do both. Let's write down, say, which one is an exothermic process? That means this one puts out heat. Okay, and if you think, well, putting out heat, the temperature should go up. So the last one, the temperature drops. So no, I'm looking for the, as the process goes, it puts out heat. Now, what you have to think to yourself is, you know, I'm adding heat, I'm taking away heat. Okay, if I melt ice, to get ice to melt, to go from a solid to a liquid, I have to add heat. So that means ice melting, okay, is endothermic. Nope. Yeah. To go from a solid to a liquid, I'd have to add heat to that. The liquid ends up being at a higher energy than the solid. Water evaporating. If you have water on your skin and evaporates, it feels colder to you. To go from a liquid to a gas, you have to absorb heat. So if you want water to evaporate, that's also endothermic. Okay, boiling soup. Well, when I boil the soup, I have to add heat to the soup. So that's pretty much what I'm looking for. Condensing water. Actually, that's wrong. I just said I'm adding heat. So boiling soup is endothermic because I'm adding heat to it. What's exothermic is going from a water vapor to a liquid. That would be, to get water to condense, you have to heat will come out of it when that process happens. Okay, so the answer is D. Okay, without looking at any of these answers, well, I guess you got to look at it. If you're negative, you're exothermic, and if you're positive, you're endo. So negative exo looks like my answer. I don't have any positive endos, so B. The chemical reaction that absorbs heat from the surroundings is said to be, if you're absorbing heat, you're endo, and your delta E should be positive. So A. How many joules are equivalent to 37.7 calories? Okay, a little bit of dimensional analysis. 37.7 calorie, and 1 calorie is equivalent to 4.184 joules. So I got 37.7 times 4.184. The answer is 158 D. Joules. And the carries cancels. Okay. Salt A and B were dissolved separately in 50 milliliters of water in a coffee cup calorimeter. The water temperature is measured and recorded in this table. What's a statement of this data? Okay. Initial, final. So I would just look at this and classify the delta H as being positive because this temperature dropped. This one I would classify as being negative, exothermic. Okay. So salt A was endothermic. Salt B wasn't endothermic. They both were an endothermic. Nope, that's all wrong. So the answer is A. Only A was endothermic, which is a positive H. Okay. Really like you to know potential energy diagrams. And it's so hard for me to see what I'm recording, so I'm just hoping that I'm in the right area. Okay. This reaction, if I just wrote on this, the reactants are on the left. They're higher than the products on the right. So my H, this is your H right here, your enthalpy, it dropped down. So that's my delta H. The change in H is negative. Okay. The one thing you'll see up here is from here to here, that's called your EACT. This is the energy you have to invest to break bonds in the reactants. The energy you get back in return, breaking bonds is always endothermic. Making bonds is always exothermic. Well, I made more bonds than I broke, so the overall H is negative. Okay, and at the top, that's called your activated complex. Okay, it's the highest energy your reactants and products reach. Okay, and the products have higher potential energy, so C and D are wrong, but the delta H is negative, not positive, so the answer is A. Okay, now we have this diagram. Okay, without even going, I'm just going to look at a few things. My energy of activation went from 20 to 80, so EACT is equal to 80, and that'd be kJs. Okay, the delta H, I went from 20 to 40 and it went up, so my delta H is a positive 20 kJs. All right, and the reaction is endothermic because it's positive. So EACT is 80, delta H is positive 20 and endothermic. A looks correct. What's wrong with C? It's not exothermic, it's endo. Okay. A catalyst. When you add a catalyst to any reaction, it takes the energy of activation and lowers it. Effectively, it makes the reaction go faster. So this is with a catalyst. So the definition of a catalyst is something that lowers your EACT. Okay. Catalyzed endothermic. Okay, so endothermic, I need the products to be higher than, so that's out. That's endothermic. There's the catalyzed reaction. And so what I'm looking for right there is 4. And the delta H on that is positive. That's endothermic. The delta H, what was wrong with this? The delta H was negative. So this one was exo. Okay, X, Y, and Z, the addition of a catalyst to the reaction would cause a change in which of the indicated energy differences. Okay, it's going to lower this. So my line is going to go here. A catalyst does not affect your delta H. So a catalyst doesn't affect the delta H. In this diagram, it affects the EACT, so it's definitely number 1. But it also affects the from the top to the bottom. So the answer is 1 and 2. D. And that's everything on interpreting graphs. Okay. This reaction up here, I got a negative delta H. So this is exothermic. And heat is, the word we want to use is evolved. Evolve means it's giving off. Absorb means it's endothermic. So I got exothermic and evolved. Okay. The value for this reaction now, what we're getting into now is using delta H as a in dimensional analysis. So we're going to look at delta H quantitatively. Delta H for this reaction right here is negative 126 kJs. Now if I write this as a thermochemical equation, there is really no such thing as a negative amount of heat. The negative just tells you whether it's coming into the reaction or going out of the reaction. So all I'm going to do is say, if I put it as a product, that means that it's negative. That means that it's exothermic. If I put it on the left side, then it's positive. If I flip this, this negative will become a positive. An exothermic will turn to an exothermic reaction. An exothermic reaction will turn to an endothermic reaction if you flip it, and if it was endo, it'll turn to exo. Okay, so now I can use this as a conversion factor. It's not called kJs per mole, it's just called kJs. Well, as a conversion factor, it's per 1 mole of O2, it's per 4 moles of NaOH2, it's per 2 moles of water, and it's per 2 moles of sodium peroxide. Okay, so let's set it up. How much heat is evolved when 2 moles of NaOH? So I want to find the amount of heat in kJs. We could consider that to be our quantity, our Q. This is a delta H, so this kind of shows you the difference between Q and delta H. Q is always, delta H is always on a mole basis. So in this reaction, it's stoichiometric. Q is just an amount of heat, okay, and usually given in joules. So when we get out of the reaction, it's in kJs, okay. So I want to start with 2 moles of NaOH, and you want to make sure you label. And I want to go from a mole of NaOH to a kJ. I can do that. 126 is equivalent to 1 mole of O2. So the answer is 2 times 126, which will be 252. A. Okay, same thing. My delta H for this reaction is negative 790, so I'm going to say this is plus 790 kJs. I tend not to think of heat as being positive or negative. In this case, they could put a negative in front of this, but if you look at the word, it's already telling you that it's evolved, so they're telling you that it's negative. So you got to be careful. Sometimes they put signs on Q, which I don't really care for. Okay, the value for this is 790. What's the complement when I get? If I get 0.95 grams of sulfur, and I want to calculate the kJs, just dimensional analysis. So I'll go gram to mole. So sulfur is 32.07 to 1. And then mole to kJs. The delta H is 790. It's exothermic. So it's asking you for the enthalpy change. So they're going to put a sign on this. So since this is negative, I'm going to say that it's a negative amount of heat. It's going to go down. So I'm going to put a sign just because they're not telling you that it's going up or down. And then from the equation, that's per 2 moles of sulfur. So I got 0.95 divided by 32.07 times 790 divided by 2. Now when they said enthalpy change, I will go ahead and say, okay, it's a negative because it's exothermic. And that gets me 12. So they're looking for a negative 12 here, and they give you a positive. I will not do that on the test. I don't like doing that. I just like to say it in words and have you understand it in words. Okay, this is exothermic, so this is plus 184 kJs. Okay, what mass of AOH? So they want you to convert the grams of HF. Okay, and I want to produce, they're giving you 345 kJs of energy. Now, one thing I might take a look at real quick. This is in the mole map. So if I go from moles of reactant X to moles of reactant Y, there's a box down here that we did not get to before we left on COVID-19. This is kilojoules. So this conversion is your delta H of your reaction. And it depends which reaction you're starting at. So in this one, moles comes into play. If you go to grams, grams is always the molar mass, and that's always gram per 1 mole. To go back to grams of Y, of X, you would use the molar mass of X. So this would be grams of X per mole and per 1 mole. as a conversion. So here's where we've been going. This is our delta H. So if I know amount of heat, I can divide it by moles to find out the heat, the delta H. But this Kj is just a Q. It's an amount of heat that we're getting to. So that's what we're doing in these equations, is we're going from grams to moles to kJs, from kJs to moles to grams. Everything else, all your other boxes are up here. Liters of gas, liters of gas, liters of solution, liters of solution. But I'm just focusing on that part of the mole map. So if I look at this one, I'm going from kJs to moles to grams. And I can do that with my knowing my delta H. So kJs, it is important to label. If you don't label that this is HF, you're going to be in trouble, because that's where you get your coefficient from. Unlike molar mass, you put in the number of moles there. 4 moles of HF is equivalent to 184 kJs. Now, this is why I don't like messing around with the signs, because if I put a negative in this, it's impossible to get a negative amount of grams. So you notice it says to produce. That means it's exothermic, that it's coming out. So I don't really have to look at the sign on this one, or it really would mess me up, because you can't get negative grams. The molar mass for this is 20.01, and that's always per 1 mole. So labeling it, that's what it's all about always with dimensional analysis, labels. Okay, 345 divided by 184 times 4 times 20.01 equals 150 grams. C. Okay. The quantity of heat needed to raise the temperature. Now we're getting into calorimetry. So all your equations are going to be Q equals Cp times M times delta T. Here is the one big question where students get confused. They go, well, when do I know to use this, and when do I know how to use dimensional analysis? In Hess's law, in heats of formation, in any type of stoichiometry, there's no temperature changes in any of these. You know to use this when you have 2 different temperatures. So if it's asking you for like temperatures, then you know you're going to use Cp times M times delta T. All right. Quick question on theory. The quantity of heat needed to raise the temperature of a substance 1 degree is called its specific heat. Now, this would actually, I think, just be heat capacity, because specific heat is like 4.184. That's the number of joules, the energy required to raise 1 gram 1 degree Celsius. This one has grams in it. So heat capacity doesn't have the mass in it. So I would just call that one, this is heat capacity, I think. Okay. Specific heat. Specific heat is the number of joules per gram per degree Celsius. Okay, which will require the most heat to raise the temperature of 10 grams by 5 degrees Celsius. Okay, that would be the one with the highest specific heat. That would require the most joules. So I'm just going to go down these. The highest specific heat I got on here is iron. So I'm going with iron. Okay. Which of the following specific heat would show the smallest temperature change, gaining 200 joules? If you think about a question like this, something like aluminum, if you've cooked, you know it heats up quick and it cools off quick. That's because it has a very low, relatively low specific heat. Okay, what's even lower is copper. Okay, so I'm looking for something, the smallest temperature change will be the highest specific heat. The lowest temperature change would be the lowest specific heat. So in this case, I'm actually looking at aluminum. Except for the fact that they're giving me 50 grams of it. Yeah, so having more grams would give me a smaller temperature change. So I would go with the 50 grams of aluminum. Okay. Equal masses of two absorb 25 joules of energy. Boy, I hate these questions. If temperature of A increases by 4 and temperature of G by 8, one can say what? That means temperature B went up by more, so temperature B has a lower specific heat. So I would say that A is double B. The one that went up the least has the highest specific heat. The one that went up the most has the lower specific heat. And that's the way I would read that. Okay. Happier just to do a problem than get into all this theory. It's talking about temperature changes, and that's my big key to say, hey, calorimetry equation. I'm going to use it. Okay. It wants to know how much heat, so it wants to know your Q. This is not water, this is lead. So it gives you a specific heat of lead. So it's 0.13 joules per gram per Kelvin. Now they threw Kelvin in there. That's nice. Love it. And 15 grams of lead. And the temperature change would be 15 degrees Celsius, which equals 15 Kelvin. Okay, so I'll just stay with Kelvin. A temperature change in Kelvin is the same as your temperature change in Celsius. So you get 0.13 times 15 times 15. 29.3 degrees, no, joules. So we're going with 29 because we got 2 sig figs. All right, good. I think I'm gonna, let me do a few more, then I'll click it off. Okay. Again, these are all Q equals Cp times M times delta T. If you want to, you can create a list. Q is 29 joules. Mass is equal to 15 grams. And the temperature change is 22 to 37, so your delta T equals 15. Looks a lot like the last problem. What's the specific heat? So now they want you to solve. Geez, I think I know it's going to be 0.13. Solving Cp, it's Cp equals Q divided by mass divided by delta T. So I would put in 29 joules, the opposite of the problem we just did. 15 grams on the bottom, and times 15 degrees, and that's equal to 0.13 joules per gram per degree Celsius. Okay. A sample of water at 69. Okay, this is where it helps to draw a picture. I have 2 cups of water. Okay. This water is 69 degrees, so I got temperature initially equals 69 degrees. Okay. Is added to an unknown amount of water, so mass equals question mark.